Okay guys, we looked at electricity yesterday, and we described electricity as the motion of electrons. So in other words, we have a material that allows for electrons to move freely. Now, materials that allow for electrons to move freely are usually have an excess of electrons, but not so much so that they actually want more to fill up their energy levels. So the metals are usually, in that case, they have only 1 or 2 or 3 extra electrons, and so they are very generous to give them away. Okay, and that is why in metallic bonds we have this flow of electrons, giving electrons to other of the atoms, and as a result they are able to easily transfer their electrons. And when electrons flow, electrons themselves then contain energy, and that energy can be converted into any other energy. So any energy can be converted into another energy, and electric energy is then called electricity, and we measure it in volts. So a volt is the amount of joules per coulomb. Joules is energy, and coulomb is a group of electrons. So joules per coulomb is volts. So if I'm measuring volts, I'm measuring how much energy does a little group of electrons have. Now, in electrochemistry is now using electricity to create a chemical reaction, because a chemical reaction is also, when it comes to redox reactions, it's about sharing, giving away electrons to other elements. So an electric current can do that. It is the transference of electrons. So electricity can do it. Or we can do the opposite. So we can either use electricity to create a reaction, or we can use a reaction to create electricity. Okay, and we'll look at that. So let's just first look at redox reaction. So an element that has that is in a, is it in a covalent bond? How can I say it? An element like oxygen, pure elements that are just themselves, like oxygen for example, has what we call an oxidation state. So there's an oxidation state, okay, of 0. The oxidation state. So pure elements like oxygen or hydrogen or iron or sulfur, or whenever I just look at a pure element that's just by itself, its oxidation number is 0. Okay, but if it is in a bond with another element, its oxidation number, the oxidation number is the number of electrons that it had received or given away in order to be in that reaction. So for example, for H2O, okay, the hydrogen is giving away 2 electrons to oxygen. So oxygen has an excess of 2 electrons, and therefore he's 2 negatively charged, and hydrogen has each hydrogen gave away 1 electron, so it's one positive charge. Sometimes, most of the times, hydrogen is 1 plus, but there are some cases in which he actually gets the electron, and that is if he's in a compound where like sodium hydride. Sodium wants the electron less than hydrogen wants it. Is electron, remember, measure of how much it wants an electron? It's electronegativity. Okay, so hydrogen desires that electron more, so he ends up getting the electron instead of sodium, which would give it away then. Okay, so there are some exceptions, so it's not just always that if I'm in the first column. Remember, we're looking at the periodic table. In the first column of periodic table, these elements are always, they become 1 positive. But hydrogen is right at the top, and he's the one exception where he can either get one or he can give one away, because he only has 2 in his highest energy level. Can only take 2, I mean. Okay, so that's the oxidation number. Now, if in a reaction, for example, if I were to take the exothermic reaction, hydrogen plus oxygen, to produce water, H2O, okay, notice that I went from having a 0 oxidation state for both of them to having a positive and having a 2 negative. Okay, and this is called a redox reaction. So a redox reaction is a reaction where my oxidation state changes. And what had happened in here is that there was an exchange of electrons. Okay, so that's a redox reaction, when there was a change in exchange in electrons, causing a change in the oxidation state. So for example, what reaction can I show you that's not a redox reaction? So for example, hydrochloric acid plus sodium hydroxide. Okay, an acid and a base produces what when they react? Salt and water. So the salt is the sodium chloride and H2O. Okay, now let's quickly look at the oxidation states. None of these elements are in their pure form. You see, so none of them have a 0 oxidation state. So this one here is a plus. This one, this is the hydroxide ion, but let's just look at oxygen as 2 negative and hydrogen as 1 positive. Sodium is 1 positive. Sodium stays 1 positive. Chloride is 1 negative. Chloride is 1 negative. Hydrogen here, there's just 2 of them, but both of them are, it's not H2 like H2 in that case. Both of them are 1 positive and 2 negative. So notice that oxygen, that none of their oxidation states changed. They're still all the same. So this is not a redox reaction, which means at no point was there actually an exchange of electrons. Okay, the bonds were broken, and now just different elements were attracted to different other ions, was attracted to different to other ions. Okay, so it's not always that we have an exchange of electrons creating a reaction to take place. Now, in a redox reaction, there is, the reason why it's called redox is because we have a reduction and we have oxidation. Okay, reduction means your oxidation, the oxidation number decreased. That's why it's called a reduction. Your oxidation number decreased. So for example, I went from 0 to 2 negative. So in a reduction, I gained electrons. Now this is where people usually confuse it. So because reducing sounds like I am losing something, and yet I'm actually gaining something. Reducing is about my oxidation number has reduced from being positive to negative, or being -1 to being -2, or being going from 0 to -2 in this case, for example. Oxidation is when your oxidation number increased. So if I'm oxidizing something, I'm giving it a higher oxidation state. Okay? In other words, you're losing an electron, because your oxidation number is positive when you've lost electrons. So it's increasing if you're losing electrons. That makes sense, no? Okay, so here's an example of a very simple example of what is being reduced. So which one is undergoing reduction in this example up here? Oxygen is going from 0 oxidation state to 2 negative. So he has his oxidation number has decreased. So he's been reduced. Or he's received electrons, so he has been reduced. The other one, it necessarily has to be oxidized, because what happened to those electrons? They were given to, or they came from hydrogen. Let's look at another example. Let's say we have a metal like sodium plus hydrochloric acid. Okay, what do we get when we have a metal with an acid? It was the only one that didn't produce water. All acids reacting with some metal compounds produce what? Always salt. So the salt is easy, it's sodium chloride. Okay, and then what's left? Just hydrogen. Okay, so notice here, let's quickly write out the oxidation number. Compound on its own, 0. Positive, negative, 0. So notice we went from sodium, became sodium positive, which means that on this side, okay, I gave away my electron. So this one minus an electron will give me that one. But we never write an expression with negative electrons on the one side. Okay, we rather take it to the other side and say sodium can break up into a sodium ion and an extra electron. Does that make sense? So I can break up sodium into sodium, one positive ion, and then one extra electron. Now on the other side we had hydrogen, which was a positive, and that became hydrogen, the diatomic molecule. Okay, now again, this one is positive because hydrogen gave away an electron. Okay, so obviously the electron goes to the side with the cation. Okay, it's added to the side with the cation, or with the higher oxidation state. Okay, and now you can see this is actually what happened is these two reactions happened at the same time. We must just be careful here, because he has two hydrogens. In other words, we must have two hydrogens here, but two hydrogens will give away two electrons. And this now actually gives me a way of, and you'll notice the chloride didn't change. It's negative on this side and negative on that side. This gives me a way to balance my equations, because now I need to have these two equations happen at the same time. But to do that, this one is going to need an electron. This one is giving 2. So I just multiply this whole expression with a 2, and then I write them together. So 2 sodiums plus 2 hydrogen cations, but we won't write the cation. We will include this is, what is it called? The spectator ion. The spectator ion is the ion that didn't change, yeah. So we'll include, this one is an ion on its own, so he must get a spectator ion, okay? We'll produce, in the end, 2 sodiums with the spectator ion, because now it's an ion, okay? Plus hydrogen, and there we've balanced our equation. You can see. So there's much more complicated equations that are very easily balanced using this reaction. Let me look for one. Okay, here's a nice one. Rusting. Rusting is when we have iron plus oxygen producing, now iron, this specific iron we're going to look at is going to have 3 electrons that he can give away. Okay, so in other words, it will produce iron that gives away 3 electrons, and oxygen, which needs 2 electrons. Now, these two can't react like that. The oxidation number, when I multiply this little subscript with the oxidation number for both, they must cancel out. So for example, look at my oxygen up here, my water. 2 positives and 2 negatives. So in other words, 2 times positive and 1 times 2 negative, it gives me the same answer. Okay, so I need to know what little foot script I'm going to have, and hopefully you can see you're just finding the lowest common multiple for both of those, which is 6. So this one must be multiplied with a 2 and this one with a 3. So now I have 2 times 3, I've got 6 positives. 3 times 2, I've got 6 negatives. Okay, that's how you find that. How many of each? Okay, but on this side we have our oxidation states are 0. Okay, so let's quickly write our redox and our reduction and oxidation reactions. So which one was reduced? So reduced means you gained electrons, or you can look at the oxidation state. Which one decreased? Which one's oxidation state decreased? Oxygen. Oxygen went from O2 to becoming O2 negative. Okay, so what happened? On which side am I adding electrons to balance it? On this side, yes, plus 2 electrons. Okay, and notice there's 2 oxygens on this side. 2 oxygens is going to need 4. So on this side we have 2 oxygens. On that side we must also have 2 oxygens. But now notice, if I have 2 oxygens, how many electrons am I going to work with? I'm going to have 4 electrons that's going to be needed to make 2 oxygens into 2 oxygens anions. Does that make sense? That's a redox reaction. The oxidation reaction is when my metal became a cation, 2 positive, and again, as we said, we're adding the electrons on the cation side. So there were 3 electrons added here. Okay, now once again, I want to balance this equation. There's no spectator ions, which is great, but now if I wanted to get these 2 equations to happen at the same time, I need to make sure that on the left hand side and the right hand side I've got the same number of electrons. How can I do that? Any suggestion? Multiplying with what? What can you multiply this one with and this one with? It doesn't have to be the same number, but I'm going to multiply one number throughout so that the electrons equal the same. With 3 and 4. So again, we look at the lowest common multiple. In other words, what's the smallest number that 4 and 3 can divide into? Make sense? And that would be 12. So 4 times 3 is 12, so I'm going to multiply everything with a 3, and here I'm going to multiply everything with a 4. And now that is equal. So on this side, when I put everything together, again, oxidation states of 0 are written by themselves. So 3 oxygens, or let's rather say 4 ions plus 3 oxygens produce, and then these 2 get combined. So there's now 4 of these and 6 of these. But notice, for every 2 of these, I'm going to need 3 of these. Do you notice what I'm saying? So for example, this one, let's write it like this. Let's see if these two are going to be combined, then obviously they need the same coefficient for both. So this one's coefficient is 6, that one's coefficient is 4. What is their, and in this case it would be their greatest common factor. What is the greatest common factor for both of these? 2. So there'll be a 2 in front, and then we'll take the coefficient divided by that 2 to get the subscript. So 4 divided by 2 is 2. Oxygen is 6 divided by 2 is 3. But we already knew that from here, where you could have just used them, and then you would have just divided the coefficient with those numbers, and you should also still get the same answer. Okay. And there is the balance equation. Let's quickly check. 4 of these, 4 of those. Okay. Oxygens, there's 3 here times 2 is 6. There's 2 here times 3 is 6. We'll balance it. Nice way. Well, it would have been for me easier to balance it from this, but I'm just showing you the method, and no matter how complicated this top part is, the bottom part is fairly, or doing it through the redox, these are called half reactions. Doing it using half reactions is actually always the same. Sometimes more complicated than just doing it by inspection, but it's never more complicated in any one question, or between two different questions. They are usually very simple. Okay, so let's move on from there and then go into how this is now actually used to generate a current. Okay, so if I were to have a metal here, and let's try and use this metal. Let's say I've got a copper and zinc. Two metals, a copper and a zinc. Now, copper has a certain desire for electrons, and zinc has a certain desire for electrons. But for now, we just have the copper here by itself, and my zinc. So if I were to now connect these two with a conductive material, okay, and I were to put a voltmeter reading in, a voltmeter in there, it is likely that electrons will flow from this one to that one. Okay, but here's the problem. Or it might go from this way to that way. We'll see now which is more likely, electrons to flow from zinc to copper or from copper to zinc. We'll have a look. But the problem is, the moment an electron is released in that direction, this whole thing becomes electron poor. He's lost an electron, making this bar positive. And the moment it becomes positive, it attracts negative particles. So now it will, that electron that it donated, it will immediately attract back.
But isn't it using?
So if this one has a desire for electrons, okay, it's pulling that electron away. But the moment he pulls them away, this one becomes positively charged and he attracts it back immediately, so that there's no flow of electrons. Yet, we'll get to how it will flow, okay? Let's say it happened at this side. The moment he gets an electron, he now has an extra electron, making him negatively charged. And because he's now, as a substance, negatively charged, he's got extra electrons, he will reject any further electrons, or even that electron that he just received. He would want to reject it, okay? Which just, again, it immediately stops the flow of electrons. So that is why in this case, this circuit is not closed. Because in order for it to flow, we need to somehow, if he gets an electron on this side, he must be able to donate away a negative charge so that he is not himself excess negatives. And the moment this one gives away an electron, he must be somehow able to get a negative charge. In other words, an anion must somehow be attached to copper now, so that he is not anymore excess positive charges. Okay, does that make sense? And that is why, in order for this thing to react, we put them in a solution called electrolyte solution. Sorry. Both of them are in an electrolyte solution. So what an electrolyte solution is, just it is a solution with anions and cations. Okay. Sorry? It's water, yeah. It's water with anions and cations in it. Okay, what happens now is if, and I don't know, I can't remember which one is a copper or zinc that gets it. I'm just explaining now the concept, who's going to give away or who's going to attract it. It depends on which one has the higher ability to oxidize or reduce. It depends on which way you look at it. So if I have the ability to reduce, it means I'm able to give you electrons. But you also have an ability to reduce. All elements have an ability to give electrons. It now just depends on whose ability is better at giving electrons. Because if I'm better at giving you electrons, then you are better at receiving them. It's just how it works. It makes sense. So electrons will flow from me towards you. Now when that happens, you get extra electrons. So let's forget about what this is. All I'll say now is the one would be the anode. That is the one that would donate his electrons in the outside circuit. He becomes the anode. So electrons go from him towards the cathode, which is the one receiving the electrons in the outside circuit. So the cathode becomes negatively charged because he's getting electrons. So what happens in the solution, because there are now cations and anions, the cations are attracted to this bar.
So,
yes.
But how can it? Isn't.
So do you notice a cation is positively charged?
Yes.
So because this one has now extra electrons, nice, I can come and get electrons from you. I am negatively charged, so I'm attracted to I'm positively charged. My cation is positively charged.
The cathode is negatively charged.
Yeah, it's not called cathode because it's negative. It's called cathode because it attracts the cations. Okay, and the anode is called the anode because it if I give away electrons, I release K. Now I don't know why it's called cathode. What I do know is the anode is the one donating electrons. The cathode is the one receiving electrons. But if I receive electrons, cations will be attracted to me, because I've got electrons, and cations are positively charged. They want electrons, so he's attracted to the cation is attracted to there. But the moment that happens, the electrolytic solution loses a charge. It used to now have a positive charge. Now it's losing that positive charge. And the electrolytic solution becomes negatively charged because it's lost a cation, and because it's now negatively charged, it's just attracting that cation back. So nothing's happening. Do you understand?
But something is supposed to be happening.
It is, but it's not yet.
Oh, yes.
Because our circuit is not complete. Okay, so the same happens on this side. So on this side, I'm giving away electrons, which means that whatever the anode is made up of, It's a metal because it has to. So in other words, it is made up of some metal. Metals we usually use A for, I think. So it's made up of some metal, and now this metal has given away electrons, so it himself has become an anion, and it's given away its electron. So this electron goes into the circuit. This anion, so this is the anode. The anode gives away an electron, but then is left with an anion. And as a result, the anion, no, what am I saying? It's a cation, isn't it? Anion is negatively charged, sorry. Yeah, it doesn't matter. He's negatively, no, I'm just confusing myself with the A. Okay, he's giving away a cation, okay, and so the cation is released into the electrolytic solutions. Make sense? But now all of a sudden, the electrolytic solution has got extra positive charges. It's positive. And now because it is positive, it's going to attract back this electron that was donated. Do you understand? So again, we have a problem. The current is not flowing on either side. Whatever is happening, it causes an attractive force back to whatever it donated. So that is where the salt bridge comes in. So you'll notice that on this side I am positively charged. So we want our salt bridge to, on this side, donate for us something that will satisfy that bridge. Now salt is always a cation and an anion. I'm positively charged. Which ion will I want? No, cation is a positive charge. So I will get on this side the anion. On this side, the electrolyte is negatively charged. So I've got an excess of anions. So I need on this side to be donated a cation from the salt solution. And now finally my my circuit is complete.
So in other words, without a salt bridge, there's nothing that's going to happen.
Yes. Nothing will happen. Okay. Does it make sense? Okay. Now your salt bridge doesn't always have to be a salt bridge. It can be, there's different ways of allowing anions, because for example on this side we have an excess of anions, on that side we have an excess of cations. So one way that they also do these, and this is called an electrolytic cell, no, it's galvanic cell, no? Electrolytic is,
No, the first one is a galvanic cell.
yeah, this is a galvanic cell. But if I have here a porous membrane, now what a porous membrane is it doesn't allow for the solids to pass through, but it does allow for anions to pass through. And since on this side I have a negative charge and on that side I have a positive charge, the two charges can interact to and can go through to react on either side, and also allow for a current to flow. So here on this side, instead of having a salt bridge donate the ions I want, I have this porous membrane that just allows ions that need to go from this side, because now I get a negatively charged. So the moment I get a negative charge, a positive charge on this side, I mean, the negative charge can go over to satisfy that positive charge. Does that make sense? Okay, so now it's just a process of recognizing, well, which one will be the anode and which one will be the cathode. Now one way of finding it out is by looking at a table where they have recorded what the reduction potential of different ions are. Okay, and an ion now being something that goes from one energy, from one oxidation state to another oxidation state, and they've done this. Now the way in which they've done this and how they got those values is they compared it to another, a standard. They chose a standard as their, to compare it with. So remember what I said yesterday about the voltmeter. A voltmeter measures the difference between 2 points. Okay, now if I wanted to know what voltage can be produced by a certain substance, I need to compare it. I need to compare the difference with another substance. Okay, so I need to create a galvanic cell here, and in it I need to compare it with a standard, and the standard that they choose is hydrogen. So this is how they do it. They have a little test tube that looks like this, and they pump hydrogen gas my salt bridge. They pump hydrogen gas in here. That's a little platinum plate that acts as a because hydrogen is not a conductor. Okay, so hydrogen cannot freely give electrons, let electrons flow. So we have to have something that hydrogen can give his electrons to that is conductive. And that is what they do, is they use platinum here. And as a result, it's not platinum that is actually giving its electron, but it's hydrogen that's coming in here and giving its electrons. So in other words, then we get whatever this substance is on this side, we get a voltmeter reading there. And that is what the voltmeter reading that's been recorded in this table. Okay. Now, this table is also slightly related to our periodic table in the one sense. Which element do you guys think has the strongest ability to get electrons? Okay, now if I get electrons, I always just have to figure it out. If I get electrons, my oxidation number is decreasing. So in other words, I am reducing. And which means I am oxidizing you because I'm increasing your oxidation number. Does it make sense? Which element has the biggest oxidation ability? So oxidation, or if I say the oxidation ability, it means my ability to oxidize you, not my ability to be oxidized. If my oxidation ability is my ability to oxidize you. Which element, in other words, is the best at getting electrons? Sorry? Fluorine. Fluorine is one of the elements that has the strongest ability because of its desire, its electronegativity. So if we go to our table down here, notice who's right at the top, okay, is fluorine. You see, he's right at the top. And notice how the table is structured. The table tells us that as I go up, I have increasing oxidizing ability. In other words, my ability to oxidize you, my ability to go from being a cation or from being reduced myself. Okay, in other words, receiving electrons myself. Okay, so based on that, that's loosely, and then so this value that I read there is the voltmeter reading that I will see if I was connected to hydrogen. Now let's say so if I'm 31, what's the difference between your age and my age? Yeah, but what's the answer? Work it out. I'm 31. I don't want to know how old you are. I want to know, because let's say I'm the standard and we want to see what is the difference between your two the two of your ages, okay, without knowing your actual age. Only knowing my age, so I'm the standard, so we're going to compare to me. Your age compared to me, what's the difference? 11, okay? And if we take my age minus your age, we'll get 11. Okay, what do we get if we take my age minus your age? 31 minus your age. Don't tell me your age.
I think it's
12. So what is the difference between your two's age? 1. Do you see? Without knowing your two's age, by taking the difference here and taking the difference there and then taking that difference and subtracting it, we get the actual difference between your two. So we can use this table without comparing two things directly with each other. I'm comparing it to the standard, there's the one value, and if, for example, someone is older than me, let's say we take someone that is, if you take my age minus their age, you get a negative answer, because we're taking 31 minus a bigger number, and let's say we get an answer of 5, okay? The answer is negative 5, because they're bigger. Now we take your age minus the difference between them and me, not your age, the difference between your and my age, which was 11, minus the minus 5. This gives them a plus, yes, so it's 16. So the difference between your age and their age is 16. Do you understand? So the sign here is very important, because the sign would now mean, so if I'm positive, this is positive, it means I have a better reducing ability than who? If my sign is positive on this table, my reducing ability is better than whose? Okay? It's better than the standard, and the standard that is used is hydrogen. So, for example, if hydrogen and fluorine is in an galvanic cell, who will be getting electrons? Fluorine, because his reduction potential is positive, which means he has a better ability to, his oxidation ability, he's got a better ability to take away electrons from hydrogen. But if we go down the table to the very last one, sorry, this is a new table, this is just the same table upside down. Lithium, for example. Lithium is -3, which means compared to hydrogen, lithium would be donating the electrons because it has a negative. So everything is just compared to hydrogen. And obviously now, if I wanted to know what would be the voltage between any two elements, I don't need to go and compare the two elements directly with each other. I just take their standard electrode potential and the other one's standard electron potential, and I subtract the two from each other, and that will give me the one. So if that's the case, let's now go and look at our original example, copper and zinc, which is just a copper zinc cell, is a very popular one. So let's see, and I'm going from a bar of copper, which means I'm going from copper with a 0 oxidation state, it's pure copper, and a bar of zinc, so it's again pure zinc, 0 oxidation state. So let's try and find them on here. I don't think you guys can see. Let me increase it a bit. Okay, so you see copper here. There is copper, but this is copper with only 1 electron to give. That's not the one we're looking for. We're looking for copper with 2. Here he is at the bottom. Okay, so this one compared to hydrogen will have a voltmeter reading of 34. 0.34 I mean. Okay, and now zinc, I'm still looking at zinc. Have I passed it? No, I think zinc is a bit higher. You see zinc? No, not yet. So it must be lower. There's the copper, actually quite close together. Can remember. Oh, there it is. Zinc. It's negative 0.62. Now let's just try and reason it out. Don't try and remember. So the higher so the 1 is better at hydrogen. 2, if I'm higher, I'm closer to fluorine. Now fluorine is very electron hungry, he's very strong at attracting electrons. So which one between these two are strong at attracting electrons? The copper, the one that's higher, is strong at attracting electrons. So where will electrons be flowing from? In our, it will be flowing from zinc to copper. So in my original explanation, where was I? In my original explanation, I was giving the electrons away at copper side, but no, that's not going to happen. Copper is higher, or I used, instead of using hydrogen, I use fluorine because I know fluorine has the desire for electrons. So the closer I am to fluorine, the more likely I am to give away electrons. So I'm just going to, because I've already named anode and cathode and things like that, I'm just going to make this one the zinc and that one the copper. Okay. So in other words, if this is now a normal zinc copper, then this one will be the anode, because from the zinc is now donating electrons. His attractive ability for electrons is not as strong as copper's. So what is going to happen at the zinc cell? On zinc's side, we'll start with zinc, but zinc will then give 2 of his electrons. So in other words, zinc will give away 2 electrons and become zinc 2 positive. Okay? So what's happening is the electrons go one way, and the zinc ions are now released into the electrolytic solution. Now we'll look at how it's going to get, what is going to happen with on this side in just a second. But now here, let's follow the electrons. So the electrons flow. They are measured in the voltmeter, exactly how much energy they have, and then down here we are electrons are donated at the cathode. So at the cathode we now have extra electrons. So here at the end we've got electrons saying, hey, I need positive charges, come get me. Okay, so we have electrons on this side, and so electrons are added to cations. So we have copper 2 ions that's now in the, here's my copper ions are in the solution, and they are now being donated to the copper staff, the copper electrode, okay, which is now called the cathode, yeah?
But because electrons are flowing from zinc to copper,
yes,
copper now becomes more negative.
Yes, that's why the copper electrode itself now has a negative charge. So it is attracting positive ions out of the solution onto it. So on this side, what is happening at the cathode side is copper, pure copper is forming. Okay? So what will we actually see happen there is copper is forming here. So literally this electrode is being plated with copper. It is getting heavier because as time is passing, electrons are coming from this side, ions are taken from the electrolyte and now congregating on here. But what do you think is going to happen at the anode? The exact opposite.
Yeah, so it will be less mass that side.
it will be less matte. So what will happen on that side, it will look like it's rusting. It is eroding, it is releasing, so little holes are starting to form in this thing as it is releasing zinc ions into the solution. Does that make sense? Okay, now the problem is we can't have solution. So originally my electrolyte solution had to contain some copper ions. Because it's a solution, it had to. So something like copper sulfate. Copper sulfate is a common electrolyte used in this cell because it has the coppers, and now the copper is taken out. So now all of a sudden we have a sulfate, and the standard solution for galvanic cells is 1 mole per cubic decimeter. Okay, just the standard solution. But what's going to happen after some time? Okay, the coppers are being taken out of the system, so the concentration will be reduced. Now from here we now need to be donating from this salt bridge because I'm donating cations to the electrode, the salt bridge needs to donate cations back. And so something like potassium sulfate is often used in here. Potassium sulfate, the potassium will now be donated in here as a cation. Okay, but I suppose it could be copper sulfate. I don't know why they don't make it copper sulfate, but yeah, I don't. Probably no, I don't know. Anyway.
Isn't it because then if they donate copper into the sulfate and it becomes copper sulfate, the electrode will continue to take away the copper.
But that's what we want. So that's why I'm saying, like, why don't I want the thing to continue? Because I want. No, like for example, that's how a battery works. The reason why a battery eventually loses its voltage, or battery becomes, what do you say in English? Pap in Afrikaans, battery flat, yeah, is because the solution that contains the let's say it was copper sulfate has ran out of copper. It doesn't have that ion to give anymore in here. So that's why I'm saying I don't know why this thing doesn't just donate more coppers in here. But eventually he will also run out. I mean, so it's probably just cost-effective way, or the way copper sulfate may be the way in which, because this is usually a jelly substance, like a jelly-ish substance in here, or it's a watery solution with sponges here in the front to only allow for the cations to come through. It's different ways in which the salt bridge would work, and maybe copper sulfate is just not a good salt bridge. I don't know. I really don't know. But anyway, on this side, potassium, I'll just say potassium sulfate makes a good salt bridge. Okay. Or it can be a nitrate as well. Nitrates also make good salt bridges. Okay, now on this side, what had happened is we had zinc ions donated. Okay, and so because zinc ions were donated into this solution would have started with zinc sulfate as a electrolyte solution, and then as time goes by, the potassium sulfate will donate. Because zinc has now been donated into the system, we need an anion to balance so that the electrolyte isn't positively charged. So the sulfate is again released into this solution. So in this case, we will actually see our 1 mole per cubic decimeter concentration will actually increase on this side over time. Okay, But that's basically it. If you understand this, then you understand most of it. It's not difficult to grasp from there. So let's go and look at the exam question. Before I go there, let me just explain to you quickly what cell notation is. What cell notation is writing this notation in a shorthand form, and what we will do is just quickly define this one. This one was the one that what happened to this one. He went from 0 to 2 plus, so he was oxidized. Okay, so this is the oxidation half reaction. This one went from 2 plus to 0, so this one was reduced. So this is the reduction half reaction. Now the cell notation takes the oxidation reaction, the salt bridge, and then the reduction half reaction written in the following format. So you start with, in your oxidation, with what you started with. We started with zinc. Okay? Then there was, each time there's a phase change. Now phase change is going from a liquid to a solid, or going from a solid to an ion. I'm changing the phase. Each time there's a change in phase, we use a vertical line like that. So zinc went from being zinc to being zinc 2 plus. Okay, then we had a salt bridge, and then we had copper going from copper 2 plus to become copper by itself. Okay, so that is what we call cell reaction. Now, if it was the case that I had different electrodes, so for example, in the example I gave you, I don't know where I did it. Is it there? Yes. Okay. In this example, where let's say this one was copper. Okay, which one was copper? If it was copper, copper is higher than hydrogen, so copper is getting electrons. The higher I go, I'll be getting electrons, which means I am being oxidized. No, so copper would be getting electrons, so copper would go from copper 2 plus 2 electrons, and then become copper positive. Hydrogen would be the one donating the electron, so he would go from hydrogen and produce 2 hydrogen ions and an electron. Okay, so everything multiplied with a 2. No, there's 2 there, there's 2 there. That's fine. Okay, so 2 hydrogen ions and 2 electrons, sorry. So this is what would happen in this half reaction. Now if I had to write it again as the one that was oxidized, first is, I did say that, we write the oxidized one is the one that increases his oxidation number, and that would be hydrogen. So hydrogen itself went from hydrogen H2 to become H plus, and then there's a salt bridge, and copper goes from 2 plus to being copper. But the problem here is there was a different phase change as well, and that phase change came through the platinum electrode. So if you had that your electrode was not made up of the substance that you used, your electrode will just be written here. So for example, it might be that you have a graphite electrode. Graphite is that thing in your pencil. Okay, graphite makes a very good electrode because he's conductive, he allows electricity to flow, but he's also very non-reactive, so he wouldn't take part in the reaction. Same as platinum. Platinum is expensive, so platinum is conductive but non-reactive. Okay, which are two of the most important properties for electrodes that are not going to take part in the reaction themselves, that we're not trying to test. They shouldn't be reactive because otherwise we're measuring their potential instead of the element that I'm trying to measure. Okay, does that make sense? So if you use a different electrode than the one you're testing here, they'll just come right at the front. I mention that because that's what's happening in this question. An electrochemical cell is set up using two half cells connected to by a salt bridge. A voltmeter is used to record the EMF reading of the cell. The cell notation is given by, and here we see we go from our copper to copper 2+, and then we go from chlorine going from 0 to negative. Okay, so chlorine itself is a gas. A gas cannot conduct electricity, and that is why you'll see here is a comma, or they could have had another straight line with platinum. So what this one will look like is typically the same as this one. We will have the chlorine gas being pumped in here, okay, and then down here where it connects with the it's probably, I think how they do it is that if I just enlarge this picture here, your platinum here will be your electrolyte solution. Okay, here will be your platinum, and here's your gas that you're pumping in. So here on that corner right there, you've got the connection between platinum, the gas, and the electrolyte solution. So everything will happen around this surface area where the gas is in contact with both the platinum and the solution. That's how I think it happens. And again, in the solution will be donated chlorine. Depends on what's going to happen. Is chlorine going to be donated by the salt bridge, or is chlorine going to be donated by the chlorine gas, the ion? Is it going to come from the salt bridge or from the gas? That now depends. Is chlorine going to give away its electron or receive its electron? Now, we can maybe think already. What do you think chlorine is going to do? Is he going to be the one receiving electrons or giving them away?
No, receiving.
Yeah, chlorine is right there on the far side. He desperately wants, and so you'll see chlorine on this table should also be very high. I'm sure he's even high, one of the highest. Second to, yeah, one of the highest. There's chlorine. It's got a very high desire for electrons as well. Okay, so very likely, and chlorine. So let's just go back to our question. Let's see what they're actually asking. I've gone past it now. There we go. Okay. Write down the balanced ionic equation for the cell reaction. So all we're going to do is take the two half reactions and combine them. Now if it's an ionic equation, it just means we're not going to include any of the spectator ions that might be included. So if I look at that, we had copper going from copper to becoming copper 2+ plus 2 electrons. And then we have chlorine going from chlorine gas to becoming chlorine, which is 1 negative plus an electron. Okay, but now I must write them as a single equation, and I can only do that if we've got the same number of electrons. So everything here is just multiplied with a 2. So this is going to be copper plus 2 chlorines chlorine gases to produce copper ions plus 2 chlorine ions, and then something's wrong. This one is wrong. This one is on this side, plus 2 electrons. Sorry, because remember, this one's oxidation state goes from 0 to negative. So in other words, he's getting electrons. This chlorine is getting the electrons. Sorry, I just wrote. They can obviously not be on the same side, these 2 electrons. So yeah, that's still true. So this is the ionic equation. Notice we're not adding any spectator ions. Now, this is what the electrode is made of. This electrode is made of chlorine, even though chlorine is not the substance of the. But notice that both of them are going to donate into the electrolyte solution. They're just donating different charged ions, but both is going to donate into the electrolyte solution. One is donating negative charges because he's getting electrons. The other one is donating positive charges because he's giving away his electrons. So if I were to draw it for you, and I would encourage this, go and practice drawing it and trying to make sense of what this is going to look like. So our gas being pumped in here, our electrolyte solution there, our platinum bar there, okay, connected to a voltmeter reading. On this side we've got our electrolyte solution there, and this is a copper bar. So let's see what's happening. Now that we actually know which one is getting the electrons, we know that chlorine is getting the electrons. Okay, so in other words, electrons are coming in this direction. So he's donating electrons. Electrons is leaving there. So copper is donating copper ions into the solution. If he's donating copper ions into the solution, then obviously from the salt bridge, I don't know if they told us anything about the salt bridge, we'll go and look. Then I'm obviously have to be getting negative ions coming from there. So a negative ion must be coming from there. On this side, electrons are reaching here, and chlorine is coming in here. Now, if chlorine is coming in here, the chlorine gets an electron there and becomes a chlorine negative. Actually, for every chlorine molecule that comes in, it releases 2 chlorine. So again, this one is getting this electrolyte is getting anions. So this one must be donating cations. This one we said must be donating the anion. So this is my cation anion salt bridge. Okay, in which direction is current flowing? If this is A to B, in which direction is the current flowing? A to B or B to A? No, A to B, because current is in the opposite direction as electron flows. Okay, so that's just a common question. Okay, so let's see. Write down the balance equation we did. Name the oxidizing agent in the reaction. Now, oxidizing agent is not the thing that's oxidation number is increasing. He's the one that causes the other ones one to increase. So he's the one whose oxidation number decreases. Which one is decreasing? Chlorine. So that answer is chlorine. With me? Chlorine is the oxidizing agent. And again, if the oxidizing agent was an ion, that's possible. In the previous question, with it could have been. So in other words, if I went from something like, so if I'm an oxidizing agent, mine reduces. So I'm going from, let's say, 0 to negative 2, or I may be going from 2 positive to 0. Now notice, if I'm going from 2 positive to 0, I'm no longer, for example, if it was zinc, just as an example, and I was going from 2 positive to 0, I'm being reduced, which means I am oxidizing. I'm the oxidizing agent. But now the oxidizing agent is the zinc ion. You can't say zinc because zinc has a 0. So do you see? So chlorine is 0. If it was chlorine negative, my answer would have been the chlorine ion. Do you understand? So whatever is the one that originally has the higher one, that's important. Okay. So name the object. Calculate the EMF of the cell. Okay. So your EMF is very easily calculated. The EMF is then just equal to the electrode potential of the one minus the other one, and you'll take the bigger one minus the smaller one. Okay, now the bigger one is the one that is taking electrons. Make sense? The one taking electrons in here. Let's quickly name which one is the anode and which one is the cathode. Which one is the anode and which one is the cathode? Copper anode or cathode? The one that's donating electrons is the anode. The one receiving it is the cathode. So you'll see the one that is receiving electrons is the one that's higher on the table. So your formula is cathode minus anode. But I mean, even easier than that is just take the bigger one minus the smaller one. You must get a positive answer. So just take the big answer minus the small answer. And so if we go to our table, we're now looking for copper and chlorine. So the bigger one is 1,37 and the other one is copper 0.34. And remember, the sign is important. So it would be a positive number minus a positive number. If it was zinc, for example, it wasn't zinc, ne? It was copper. Our question is copper, it's not zinc. Yeah. So in other words, we would take 1,36 minus 0,7434. Thank you. And that will give me 1,02 volts. Come on, that's very easy, huh?
4 marks just for that. The 3 marks is for substituting correctly, and the other mark is for...
No, 1 mark is for correctly identifying which is the... I suppose 1 mark for each one of the correct readings from the table. 1 mark maybe for the formula and 1 mark for the answer. I don't know, I didn't get a memo for this paper. What is the function of PT given in the cell notation? It acts as the electrode because chlorine is not conductive. It's not a conductive substance. It cannot conduct electricity. It acts as an unreactive electrode. What are the standard conditions needed for this cell to operate? Okay, so standard conditions for galvanic cells is the temperature 20 degrees Celsius. Okay, so standard temperature, which is given in your table. Standard temperature, that's 20 degrees Celsius. Standard, I suppose standard pressure, but standard pressure is not the... Sorry, correction. It's It is 1 standard atmosphere pressure. Okay, so 1 atmospheric pressure. And temperature is standard temperature, but that's 25 degrees Celsius. And then the last one is the solution, the concentration of the solution that we start with is 1 molar. Now molar just means a capital M is molar. 1 molar just means mole per cubic decimeter. So in other words, standard condition is just 1 mole per cubic decimeter. So those are the 3 standard conditions. I just didn't think pressure was one of them. Okay. If the copper electrode is replaced with a silver electrode, what will be observed? Let's see. All we're going to ask is, well, where does silver lie in this? So let's find silver on our table. There it is. Is there another silver? Doubt it. No. So there's silver. So what do you guys think? What will we observe? I think you are not that far off, but be careful when you speak of rate. Rate means per second, and we are talking about potential difference, which is the ability to give electrons an atomic. Just because okay, yes, rate is so for example, current is the rate at which electrons are flowing, and current is directly proportionate to your voltage, yes, but since we're working with voltage, rather use the voltage observed will be less. Why will the voltage observed be less? Because between the difference between chlorine and silver is less than the difference between, and that's what I'm doing, I'm taking the difference between 2 observations. And if the difference between my new observation, if that observation lies closer to chlorine, then the difference will be less. So the voltmeter reading will decrease because the silver's reduction as oxidation potential is higher than the other one, or just somehow explain that silver's closer in its standard potential difference to chlorine than copper was. So there's okay. Now let's get to. I actually want to do another example of this because it's really fun. Oh, I thought this was weird. I didn't recognize this question. This was not the prelim question. Was it? No, this was last year's November exam. SACAI November exam. Oh, that's a lovely easy question for the November exam. Let's try the prelim paper. Okay, when iron nails are placed in lead 2 nitrate solution, now remember what lead 2 means is that lead has got 2 electrons to donate. Okay, lead 2 nitrate solution, a reaction takes place. Okay, So here they show us, write down the oxidation half reaction. So let's see if an iron nail, okay, if a reaction takes place between iron and the other one is lead to nitrate, so that would be Pb2 plus, okay, then he will, if the reaction takes place, he will get electrons. Well, let's actually just first see, we've got iron and we've got lead. That's now in reaction here. So let's see which one has the better ability to get electrons from the other one. So we go to our table. We look for iron. The one that is higher is more likely to get electrons from the other one. Whoa. Okay, so let's see Pb and iron. So there's iron. Iron has 3 electrons that he's going to give away or get. Do we see lead? I don't see lead. If they don't have lead,
Lead is Pb, right?
yeah.
Isn't it under iron?
Is it under iron?
Pb2 plus.
Oh, there it is, yeah. Okay, cool, thanks. There we go. Good. So, which one is going to be attracting electrons more? Iron. So, it can't be this iron because they're saying that it's pure iron. Iron nails. A reaction takes place. If it's so in other words, that in lead must be giving electrons. Is it? Wait, let me just quickly think. Yeah, I think it is true. Okay, so in other words, let's just see, it's iron 3 plus. So if iron gives away electrons, but that's not likely. So between iron and lead, sorry, not iron, iron 3 and lead 2. Okay, iron is more likely to get electrons from lead. In other words, he's more likely to go to reduce. In other words, to go from 3 plus to becoming just pure iron. But that's not going to happen here because we have iron nails put in. They say iron nails are put in lead solution and a reaction takes place. So in other words, what must be happening is must be a different iron. So it must be this iron. And this iron is lower than that, so it must be iron 2.
So, what iron is that? But then that iron is lower. It's negative 0.44.
Yeah, but I want it to be lower because I want iron to become an iron so I want the lead to take my electrons because I've got pure iron and I want to go from pure iron to iron and electrons. Now I can't, if this is iron 3 plus, he will take electrons from lead. and then iron 3 plus will become pure iron. Do you understand? So now I'm going from a cation to pure iron. And according to my question that they originally give me, they say iron nails. Iron nails is pure iron. So I'm going from pure iron, and it's put in lead solution, to and now a reaction happens. The only way that can be is if the lead is taking electrons from me. Make sense? From iron, I mean, not me.
So iron is like the boss. Iron always takes from other people.
Why do you say that?
Because the iron is like that.
No, it's not. Anything higher than this iron here, this iron 2, anything higher than it will take electrons from him.
Why do you want to take electrons?
Because in the question it tells me that if iron is put into nitrate, a reaction happens. So they're telling me I'm going from pure iron nails, to something happens. Well, what can happen with... So in other words, let's write the reaction. When iron nails are put into, are added to a lead nitrate, lead 2 nitrate. NO3, what is lead 2 nitrate? Just read the question. A lead 2, here they give it to me, lead 2 nitrate. So NO3 2. Something happens. Now the only thing that can happen is that this can become iron nitrate. Okay, now we don't yet know if this is iron 3 plus or iron 2 plus. That's what we want to figure out. And lead. That's the only possible thing that can happen. Okay, so for example, if I have A plus BC, the only thing that can be different is it can only become, and this is it can only become, if both of these two are cations and that's an anion, it can only become B plus AC. That's the only thing that can happen. Which means that we either have going from iron to some sort of cation, 3 plus or 2 plus. We must now decide which one is happening. Plus, so either 2 or 3 electrons. But we definitely know that we're going from lead 2 plus to lead. So, in other words, lead is taking electrons. He's adding electrons to himself. Are you with me now?
Yes, but I don't understand.
No.
How did you conclude that?
From here, this is look here, what's happening. This is what's happening. Would you agree? Iron nails are placed in lead nitrate solution and a reaction occurs.
Yes.
Then we get that. So can you see I'm going from 0 to, I don't know, one of these two. It can even be 1 plus. Or I'm going, but I know I'm going here, this is 2 plus to 0. So I know this is happening. Oh, is that okay? So now I must, so now look here, I know lead is getting 2 electrons. And now I just need to find out, well, who can he take it from? He can't take it from someone that's higher than him on that table. because the higher I go, the greater is my oxidation ability. The more I am like fluorine to take electrons. So I must take it from someone that's less than me on that table. Let me just use this table. So, and if I go look at lead, I then can't use 3 plus. This iron is going to have to be the 2 plus iron. There's not. Is there a 1 plus iron? No. So, in other words, in their first question is then actually quite a difficult question. Write down the oxidation half reaction. So the oxidation half reaction is the one whose oxidizing number increases. And that would be the one that goes from iron to iron 2 plus. Sorry? So Fe goes from 0 to Fe 2 plus 2 electrons. Okay, a standard electrochemical cell is set up using an iron nail and a 1 mole per cubic decimeter lead nitrate solution. Okay. So here's my iron nail, and here is a lead nitrate solution. Okay. Now, what I want you to notice here is that well, let's first see what is the solution in P. What is the solution in P? Let me just quickly think about it. Let's see what. What? It must be a solution. So in other words, it must be a lead nitrate, for example. But I want you to see here, it could. The point here is that the lead nitrate in this reaction, so notice here, even though the nail is, we know this is a lead nitrate solution. Now, even though the nail is not put in the lead nitrate solution, it is connected to the lead nitrate solution. So this lead nitrate is still attracting the electrons the way that they explained earlier. Does that make sense? Okay, so it's still attracting the electrons because it wants electrons more than this iron. So it is attracting, if this circuit is closed, it is attracting electrons. So what is happening on this side? On this side, he's giving away electrons. So what is he releasing into the... So let's just look at this whole thing, what is happening there. Let me actually redraw it. So before we actually go and answer the questions, let's put in the information and see if it is helpful. So here's my salt bridge, my iron nail connected to something. And this is PbNO3, 2. Okay, so this is where we have Pb2+. And this Pb2+ is attracting electrons from iron strong enough so that iron is giving away electrons. So this is the anode. So that's the cathode. Okay, and what is being released into this electrolyte? Yes, I'm giving away my 2+ cations. Makes sense? So we can't put Pb in here. And the reason why we can't put Pb in here is because then this ion won't be able to attract the electrons, because this ions here will attract the electrons.
But then, so, remember when you said that the iron is giving away the atoms? So Pb is collecting the ones that iron is giving away.
Yes, so but this is now what's happening on this side. So here they're calling to the electrons. Electrons are coming all the way here to here. And here now what is happening here is they're receiving the electrons on this side. And so this electrode is becoming Pb, because the 2 electrons are coming, taking Pb out of here.
So the cathode is being electrocuted with Pb.
Yes.
So that means that what's left in the solution is the nitrate.
Nitrate left in the solution.
Isn't it going to be the same as the side? Because then, if we have, let's say we have lead nitrate, you understand? The Fe2+ that is being inserted into the solution is going to react with the Pb. With the nitrate.
With the nitrate.
So then Pb is going to be left.
So again, it depends on what we are donating from here. So just because there's now NO2 ions here, okay, you're right, there's an excess of these ions, and it is just going to be satisfied with whatever is in the salt bridge. And probably in the salt bridge we do have this ion that is going to be donated in here, and that's why my answer would be that in here we have Fe nitrate.
But they didn't say so that's why we're gonna fail, because they don't say after the salt bridge has deposited whatever it deposits inside.
They don't have to say. So you must figure it out from the sketch. Come on, which part don't you understand now? Because all we did, look what I did. I followed the electrons. What happens with the electron? This one gets donated, which means in here I must have Fe2+ ions, isn't it? Okay. Now you could have in here you could have had any. It could be Fe sulfate. It's just an ionic solution. Okay? But there will be Fe on this side. It can't be Pb, because Pb will attract the electrons in this direction. And we want to be, and they've already said this is the Pb solution. So Pb will be attracted in that direction. Okay? So this must be, but so I suspect, well, let's just use the nitrate they've already given us, and then this one can maybe be a nitrate. Okay, let's see what else they ask me. And this, let's make it potassium nitrate as a common salt bridge. Okay, let's see what else they say. The solution, the solid labeled Q. What do you think the solid labeled Q is made out of? What do you think? Lead. It's a good guess. Because look, this one is being lead plated, isn't it? So why can't I just make it out of lead and it just becomes more lead plated? But you could have said graphite. Or you could have said platinum. As long as you've said a non-reactive conductive material. And now lead is not non-reactive, it is reactive, but we want it to be reactive. We are using lead in our reaction. Do you understand?
Okay, since it's being lead plated, why lead cannot attract lead? Understand what I'm saying? Because this from
no,
the
what?
solution
Okay, so this is a lead staff, okay? Or let's take it's anything. That doesn't matter. Let's for just one moment think it's anything. But it becomes negatively charged because it's getting electrons. Now once I put it in a solution that has lead ions in it, the ions will be attractive and will plate it. Now I then have an option. I can make it out of any substance that is non-reactive, or it must be lead, so that I'm still just using the lead ion. If I make it out of zinc, for example, then all of a sudden it would be the zinc attracting the electrons, and now it would be zinc connected to to iron instead of. Do you understand? Is that okay? So it's not, you can't say lead doesn't attract lead. No. Okay, there's a difference between charges repelling each other. Okay. Okay, the solution in R. R is then the salt bridge. And so yeah, I think something like potassium nitrate or sodium sulfate, or some definitely the nitrate. I would have put in definitely a nitrate. So it feels like a very open-ended word. If the cell is delivering a current for some time, what will happen to the following? The mass of the iron nail. So we close this and the reaction happens for a while. What will happen to the mass of the iron nail? Whistle? So far you're guessing, you're not thinking. So you may have to be able to explain it to me. What's happening at the iron nail? Do speak louder. No, I don't want to know don't want to know the name. What did we look at? Yeah, when we drew it. What's happening at the iron nail? Electrons. What's happening? Sorry? Please louder, so I can't hear. Cations are being given away, yes, into the solution. Electrons is given away and cations is going away. So what's going to happen to the mass of that?
Shall I explain?
Let's try you.
Actually, since the here I am the iron nails, giving off electrons.
Yeah.
But the mass at the iron mass is decreasing. So that means that now that the
Why is the mass decreasing? Because electrons are given away. Because, let me give you an example. If I give away an electron, I myself become more positive. So maybe I can attract negative ions, and negative ions get stuck to me, then I'll increase in mass. Do you understand what I'm saying? So just giving away electrons is not sufficient. You're not wrong, but because I'm giving away electrons, what's happening with the iron? You were more correct in that sense. I'm giving away electrons. Now, where did the electrons come from? It used to be part of iron itself. Now I'm giving it away, so what's happening to the iron cation? Is being donated into the solution.
Yes, so that means there's less mass.
Exactly. So it's not about the electrons leaving, it's about the iron leaving. Do you understand? Okay, yeah, that's good. Make sense? You get it?
Yes, so will it increase or decrease or stay the same?
What? The mass of the nail? Decrease. Because you're losing iron.
Oh, now that the current is flowing.
Yeah, now that the current is flowing, I'm losing iron because my iron is being donated into the electrolyte solution. My iron ions. The concentration of electrolyte P. What will happen to the concentration of electrolyte P? Sorry? Increase, yeah. I started with iron nitrate or whatever, and now more irons are being donated, more nitrate is coming from the solution, so it will increase. The mass of electrode Q, it will increase because it's plating. So it's exactly it will always, well, I know that it always happens like that, but yeah, one will corrode and become less, the other one will plate. Give a reason for your answer in question 9.3.3. Why is that one? Well, we didn't have to give reasons so far, but why will Q increase? How would you say it, Wissel?
Because of the mass of the loading, possibly.
No, why is Q's mass increasing? Just why is it becoming heavier?
So is it just electrons?
Now, electrons weigh so much that you can receive however many, so little, they are basically weightless. So yes, you're on the right track. It receives electrons, but that's not where the mass is coming from. It's receiving electrons. Now it is negatively charged. So what is it actually then receiving? Yeah, from the lead. So how you would say it is the electrode Q is receiving electrons, and then electron and lead ions from the solution that is producing a coated lead layer, increasing the mass of the electron.
It's a coated layer around graphite, etc.
If it was graphite, yes, it would have made a coated layer around only where the electrolyte is touching. The positive ions move from the salt bridge towards electrode Q. Give a reason why this occurs. positive ions from the salt bridge moves towards electrode Q. Why? Yes, but it's not attached to electrode Q. It is connected to the electrolyte. So you're right.
Oh, the electrode Q, since now it's negatively charged, it releases. So
if it releases, it would be corroding. Do you understand? So why did we need the salt bridge in the beginning? Remember I explained it little by little, things got stuck. We needed electrolyte because the electrode became charged, so we needed to satisfy that charge with the electrolyte. But the moment it took a charge from the electrolyte, then the electrolyte became positively or negatively charged. And that's where we needed the salt bridge. Do you understand? So in other words, this electrolyte is negatively charged. Why? Why is that electrolyte negatively charged? It's one of two ways. Either I got electrons, or I donated cations. No. Yes, Q is getting the cations, which means where the cations coming from? From the electrolyte. Okay. So cations are being donated to Q, and therefore the electrolyte solution becomes positively charged, negatively charged, because if donated, it's positive charges, and that is why the positive charges are moving from Q, from the salt bridge towards the electrode Q. I don't think the way you were going to explain it would have been marked wrong. It received electrons and so it was negatively charged, and therefore the positive charges moved towards it. But you're missing a step. It's negatively charged, and therefore it's taking the positive charges out of the electrolyte, and now we need to satisfy the positive charges again from the salt bridge. Make sense? So you were just missing that part. So I think you would have only gotten 1 mark for that answer. Okay. Let's move to electrolytic cells quickly.